everything's going to work out, but we'll see how it works here. Right there. Okay, I'm going to be going through another set of slides simply because it covers our processor a little bit better. So I'll post these on the e-learning site. These are the ones that come with that second book that I put that should be posted there. That's there. It's the one by Silicon Labs up there. But I'm basically going to start going through the instruction set in more detail here. And some of these slides are pretty busy. They're put together by someone that is a professional instructor, but I think she's teaching in Thailand now. She was teaching in Malaysia, the person who actually put these slides together. But this kind of goes through, this slide here covers a lot. And let me I didn't bring my little, that's there. But we're going to be going through the architecture and memory overview. This is a little bit different. This is where I think I confused people last semester because I did this for both the 8086 and the 8051. And I'm only going to do it for the 8051 in this session here. That's there. It's a simpler architecture, and the memory organization is a little bit simpler than the 8086. That's there. We've got all kinds of ways of addressing memory. Right there. We could do register addressing, which was what we were doing in last week when we did that short little lab. Remember when we were moving things into R1, R2? That's there. We could do direct addressing where we talk to memory locations directly by an address. We have not done that yet. We have not talked to memory at all. All we've talked to, that's there. We could do indirect addressing where we place the address someplace, and we'll see examples of that. Immediate constant addressing, we did that last week. Remember when we put the little number sign in there, we were actually moving the number 55 into the register. That's immediate addressing. Relative addressing is where we have the address placed someplace and we tell it an offset. We'll be looking at that. Absolute addressing, long addressing, and index addressing. But we have all kinds of ways of addressing memory. And this is a very confusing, but they give us a lot of flexibility as we address, as we start moving stuff around. What I'm more concerned about, once we get through the memory, is the various instruction types. We have basically 5 different types of instructions. We'll go through them. At their arithmetic instructions, we did an add, as I remember when we were going through. I went through and you did the add. We could do logical instructions, and or that's there or not. Data transfer, those are our moves. We were doing some moves. Boolean variable instructions. We saw that with the decrement and jump not zero right there. Those instructions are that there. And program branching, again, that's the jump not zero, our jump bit there. So we've got 8, I believe it's 8. Right, only count 1, 2, 3, 4, 5, 6, 7, 8 different addressing modes and 5 different instruction types. That's there. We're going to spend quite a bit of time talking about those right there. Okay, an instruction is made up of an opcode. Traditionally, at one point, we used to memorize the opcodes, and as I think, as I look at the final exam for this class before I came, they actually had people memorize opcodes. I'm not going to worry about memorizing opcodes. We have no need to memorize opcodes. Back when I first started learning how to do assembly language programming, we didn't have assemblers, and we would have to hand assemble our code, and we'll see some examples of this. Oh, welcome. We started without yet up there. Yeah, it's warm today. Okay. So, but when I first started, we used to hand assemble our code. And we'll see a little bit of what that looks like. But there, my very first, and I'm telling how old I am, because this was probably going back, I want to say 35 years at least, when I took my first assembly language programming class. And it was on the 8085, and we were using a board called the SPK85. It was a fairly good sized board. It was probably, I'm going to use inches, 10 inches by 10 inches, which is probably about 25 centimeters by 25 centimeters. It was a good sized board. I mean, we're talking the size of a small pizza right there from Pizza Hut. That there. And we didn't plug into a computer like we did now. We had a hexadecimal keypad, and we would enter our programs one opcode at a time, right there. Very tedious. And all the engineering students at that time walked around with the standard engineering set, the 15-inch by 12-inch calculator. It seemed like they were very large. They felt on they actually clipped onto your belt. They were too big to fit in your pocket. We'd have we'd have our little programming cards out there. So, I mean, we had the typical engineer's uniform walking around Purdue's main campus at that point. And our SDK85 instruction set card was part of the uniform that we used to carry around. That's there. Fortunately, we don't do that anymore. So, okay, the instruction format is as shown here at the bottom right here. And let me just take a few minutes to talk about this format, because this format, I'm sure, is one of those things that kind of here's our instruction right here. This is what we want to do. Now this is reversed right here. We are taking whatever's in the source and we're moving it to the destination right there. Now what we're going to be doing, a typical one, and I'm sure there's an example on this going here, is we did a move to A number 23 hex right there. So we did a move like that right there. And what that means is in our microprocessor, we have a register. This is actually also called the accumulator, the A accumulator, and we're going to move into it the number 23 hex. The reason I know it's the number 23 is this is the symbol for immediate, and we'll talk about that as we look at the instructions right there. So in our microprocessor, we're moving from right to left in this direction right here, right there. So now as we look at internal to our microprocessor, this is what our microprocessor looks like internally. That is a mess right there. We're not going to memorize this, although it's fairly straightforward once you start looking at it right there. But let's just kind of go through what we're seeing inside the processor. This is the internal architecture, what we have in there. This is the accumulator right there. Right there. That's the accumulator right there. When we say A, we're talking about the accumulator. We also have one other register inside here called the B register. Now, the accumulator will feed directly into, this is the arithmetic logic unit. This is where all the adding, subtracting occurs, right there. And it's going to subtract from temp 1 and temp 2. Now, notice that the accumulator feeds directly into temp 1. So we're wanting to do adding, subtracting. The accumulator is by far the more efficient to put at least one of our data there. Then the other one we're going to operate goes into temp 2. Now, when we write our code, we don't worry about temp 1, temp 2. We don't see those. They don't exist. That's all internal right there. But they exist. But hardware-wise, they exist right there. We don't deal so much with the ALU. That's the logic-arithmetic unit. That's what happens internally. This is the design. The program status word right there. This is the program status word. We'll talk a lot about that as we go through here. Because whenever the ALU does something, it will update the program status word. And that's, for example, if we have a command, decrement jump not 0. We saw that command a week or two ago in our time delay routine. Remember, we had an instruction that said decrement not 0, and we said, and we would say R, and I keep hitting a button here. We'll say R1 and put the $sign, which means here, right there. That's the short time, just simply means here. So that decrements R1 and jumps back to the same location if it's not there. Or we could have decrement not 0, R2, and we'll say L1 right there, and that's a location right there. Well, this decrement not zero is looking at this program start status word for what they call the 0 bit. There's a bit inside this program status word that if the result, we get almost a half a house here. We're at 3, 5, 8. Oh, you got over 50% of our students here up there. Good morning. Good morning. Hopefully everyone had a good holiday up there. Okay. All right. I'm going to continue on. Those that are coming in, just not coming in, you can catch up or watch that there. All right. Getting back to where we're at. This is the internal architecture up there. I'm going to kind of start with this slide over again. Right there. Let me erase all this here. And let me just kind of restart this slide from the beginning here. Right there. This is the internal architecture of the 8051 core. Now, this is the same whether we're talking the Silicon Labs chip we're talking about right now, or we're talking one from Intel, or we're talking one from Philips, or we're talking one from any of the other processors. This is the core 8051 right there. We've been using, the accumulator is the most important register in that. It's called the A register. We've used it there. This is the ALU. This is where all we're adding, subtracting, decrements, everything occurs there, right there. We do everything with that there. We have one other spare register over here, and that is the B register. Now, if we look at the 8086, for example, it has probably 7 or 8 different registers. It's a much more complex processor. This one is a very simple processor. It only has 2 internal registers that we're looking at right there. Now, we'll look at R0 through R7, those 8 registers, but those actually happen over here, where we've also got here that this is 260 or 256K or 256 bytes of RAM right there. So the core 8051 only has static RAM 256 bytes. That's all we have in that there. And most of those are taken out. This is where R0 through R7 actually resides on the RAM. Now keep in mind that this RAM is internal to the 8051. So one of the rules about digital electronics or electronics in general, if it's on the same piece of silicon, it can run very fast and very efficiently. As soon as I have to go off the chip onto a printed circuit board and through the packaging into another piece of silicon, things slow down. So having this RAM on the chip speeds things up and makes our circuit much more efficient right there. We also have something called the stack pointer, called the SP. That's the stack pointer. We'll talk about the stack later. And where I was talking about before was, well, notice that the accumulator feeds into temp 1, and we have temp 2 that also comes from the data bus right there. And temp 1 can come from the accumulator or elsewhere. Right there. This is where all the adding, subtracting up there. So the accumulator is our more common register that we're going to be using, especially for add and subtract. A common instruction might be add A R0. So what that's going to do is it's going to be A at the end of that is going to be equal to whatever was in A plus R0 right there. So usually the result of any addition or whatever is going to be stored back into the accumulator. Doesn't have to be, but there. The program status word is where I was at. The program status word is a particular byte and location that contains some information about the last operation. And I was using, for an example, the command decrement jump not 0 right there. We saw this command in our loop statement, in our time domain. What this simply means is it's going to subtract 1, that's the decrement, and then it's going to look at the result. If the result is not a 0, it will do the jump. If the result is a 0, it does not do the jump. How does it know it's a 0? Because the program status word has a bit in it that's defined as the 0 bit. And we'll look at that there. So a lot of our conditional jumps are going to be looking at the program status word right there. So now down here we have the rest of the processor. The bottom part of this is everything else. Now as we look at this, we'll see things such as the program counter incrementer, the program counter that keeps track of that, our program address register. This is keeping track of where we're at in our program. That's down there. We have a buffer right there where things go to before they're taken from memory. That's there. We have our logic control that controls our reset and our clock. We also have our power control register that allows us to stop and run the program in idle. In other words, go into a shutdown mode or a sleep mode. We have our special function registers right here. Interface. They talk to the location and memory, special function. And then we have our external memory right there, and then our interrupts. I'm not so worried about the bottom half of this for right now. We'll talk more about this. The top part is what we're using more right now, right there. Okay, memory organization right there. And again, we're getting back to that there. This is for the F20. We're using the F850. It's very similar. There's not a set of slides out there for just the 850. The differences are minor between them right there. But as we look at this right here, we have our program flash memory. This is our program memory. And this is our data memory internal to the chip. Now, this is where things get very confusing with this chip. Very, very confusing. Right here. There are two different types of microprocessor architectures. And we have not talked about that there. It's one of the key things that there's what they call the Harvard architecture and the von Neumann architecture. Again, I'm not there. It's in any textbook. You can Google that there. But I get the two of them confused. But Harvard is typically, and I don't have internet up here, so up there. But one of them has one memory addressing space. In other words, program memory and addressing memory or data memory are in the same set of addresses. And let me bring up OneNote here and talk a little bit about. I need to clean this up right there. So we have one set of addresses here. This is the von Neumann, von Neumann right there. And we start at location 0000000, and we go all the way down to F right there. However many. Some of this might be program memory. Some of this might be RAM right there. This is more commonly found in microprocessors right there. Microcontrollers typically use the Harvard. And that is, we have two sets of memories right here. Right here. This is program memory. This is data memory. They're separate. So our program memory is usually going to be ROM right there. Or in the case of the 8051, it would be flash programmable memory. And this is usually RAM right here. We cannot create more program memory or RAM memory. I mean, that's what they're separate. So they have separate addresses. You might want to look at these as one long street or two shorter streets. So this will start at 0000 and go to FFFF. This will go from 00 to say FF, so it's only 256 bytes right there on the chip. But we have two separate sets of addressing right there. So you need to know the difference between the two of those, and I'll give you that there. They're discussed in the textbooks, the difference between the two right there. So as we look at this, this is what the 8051 has right there. It has the two types of memory, program memory and data memory. This is typically what we would find on the 8086 8086, 8085, the i3, the i7, the AMD. Most general purpose microprocessors use this. Most microcontrollers use this. It's a huge difference between the two of them there. A lot of special function processors will be the hardware architecture. Most camera, for example, processors for digital cameras that do a lot of digital signal processing, they will use the hardware architecture. DSP chips for doing digital filtering and converting, images to MP4s and things like that will use the hardware architecture. That's there. Most RISC processors, reduced instruction set processors, will use the hardware. Most general purpose processors use the von Neumann. That's there. So as we look back at our slides right there, we will see that this uses the hardware architecture. There's two different memory spaces. This is our program memory. This over here is our data memory. Now, data memory is very complex right there. Let's first talk about our program memory right there. Our program memory is in flash. We have a series, we have it there, and it's programmable in 512K bytes. Depending on the processor we have, but there, I can't remember how much we've got. I think it's like 4K of program memory in our processor. Some of them have up to 64K right there. See, this shows going up, but you can only go up so far. FD, FF is as far as you can get. Up in here, this X is reserved or scratch pad right there. Right there. So our data memory depends on our processors right there. Internally, again, the 8051 will only receive between 00 and FF, 256 bytes, right there. The first part of this is our general purpose registers. We'll talk about those. That's at R0 through R7, and there's 4 different sets of those. We got our bit addressable memory right there. And inside these, by the way, are things such as our ports and our special function registers. Then we've got a direct and indirect addressing right there, and then we've got our indirect addressing right there. And this is our special function registers that are actually stored up here. Right, we'll talk quite a bit about our special function registers. Those are very, very important right there. Now, this is where it's complicated. Is we've got our external address space. We have to think back to the original 8051. It had 256 address spaces only. So this is what was internal to the 8051 on the top. All the modern 8051s out there, including the ones we're using, have built onto them external RAM. And they're in the external address space right there. So we now have a third address space right there. So I talked about the Harvard, the von Neumann, and now we've got a third version, which is a modified Harvard, which now has internal data right here, external data, and then the program data. So we have 3 different types of memory in our 8051. 3 different types. One is where our software goes, our program, all of our code. When we write code, it's programmed into the chip right there, and it goes into the program memory. And I didn't bring my board with me, but that's right there. But we go through and we put things into our program memory. So when you hit that little download button the other day in the lab, when we were doing the lab, this is where it went right there. It's going to go into this flash section there. We have yet to use the general purpose registers is what we use so far. That's all we used there. We haven't used the special function registers. We did that a little bit when you turned off the watchdog timer. That's in the special function register. When you write to port 1 and port 0, the ports, those are in the special function registers. When you set them up to be push-pull or open drain or configure our ports, those are all in special function registers. Right there. That's how we control a lot of things in special function registers. But also on our chip, we have some RAM beyond the 256K. And that's in an area space called XRAM, external RAM. Now, it's on our chip. If we all right. If we go back to here and we look at this one right here, this particular family right there can have up to 8K of flash memory right there. So that's our program memory. That's there, memory. That's there. Up to 12, now on bytes right there, this particular family only has up to 512 bytes. So this doesn't have a lot of bytes right there. But it's got a lot of program memory right there. So this is, and this kind of gets into our particular processor in more detail, and we'll go through a lot of this later on. And as you can see, there's all kinds of information on this particular family right here. Right here, this goes through all the various pins. And we're using all the pins. See, this is a very long detail right there. And as you can see, we're using the quad signal right there. I think this is the one we're actually using, this one right. Oh, this is probably the one we're using. So it's got 8K of flash program memory. It's got 512 bytes right there. That's what it's got right there. And as you can see, there's lots of part numbers. I'm guessing which one we're using. And the reason I'm guessing is I'm looking at the number of pins. The package we're using is this one right here. Yep. Right there. So as we're looking at this right here, so in our case, this is not very big right there. In our case, this is only 256 byte right there. Right there. But it can be up to 4096 is what it is on the F02020. So different chips have different levels of that. But some of our space is off the chip. Some of their chips have 64K of external RAM built onto the chip right there. So it just depends on the particular chip that's there. But the original 8051 did not have this. This was, on the original 8051, this was truly external. Now, the one that we're using, this is actually on the chip, but we're still having to treat it as external in terms of writing software, right there. If you didn't treat it as external, then that would mean that 8051 software from one processor to another would not work. So in order to keep things consistent, everybody that ranks an 8051 core processor will treat anything beyond the original 256 as external, even though it's still internal to the chip. So this is where this processor gets very confusing. There's 3 different address spaces. Remember this, 3 different address spaces. There's program, flash data memory, which is in the flash right there. We just remember this program. There's internal data memory that's limited to 256 bytes. And then there's external data memory that can be up to 64K. In our case, it's only 256 bytes. We've got 512 bytes of memory to work with up there. And remember, for embedded systems, you don't need a lot of memory. Up there, you do not need a lot of memory. Up there. If you're playing video games on a desktop computer, then yeah, you need a lot of memory. Up there. If you're doing word processing, you're loading things in and out of memory, you need a lot of memory. But if you're pumping gasoline or keeping track of someone's heart rate, or if you're trying to control a particular motor, those types of things, you don't need a lot of memory right there. So it is right there. So, okay, now we get into the internal data memory. This is that 256 bytes that we talked about right there. 256 bytes goes from 00 to 7F right there, or 100. Actually, this is the bottom 128 bytes right there. So this goes to 7F. So this is actually this 100 lower 20 right there. And right here, this is R0 through R7 right there. Now, we have 4 different sets of R0 through R7. Those are banks. When we write our assembly language code, we have to tell the assembler which bank we want to use. We can switch banks if we want to switch banks. So that gets us a total of 4 times 32 bytes of memory that we can address with R0 through R7. That's there. We use the default register bank, which is these locations right here. But we can switch our bank, and we'll see how we can do that too. Then we have a number of addresses that are bit addressable right there. Right there, that are bit addressable. And these contain various types of information right there. But we can address these as individual bits right there. And the advantage of addressing for individual bits is if we want to keep track of, say, if an array is full or a tank is full, and we just want 1 or 0. We have bit addressable. And then we have another group here that are just general purpose RAM right there. So those are our lower 128. And we can use those however we want. They're not defined for anything right there. The upper 128 is much more restrictive right there. These are our special function registers. They all mean different things right there. Between 080 and F8, these are also bit addressable. Now, each one of these has a particular meaning right there as we go across from here to here. Now, this table's a little funky here. This is 80, this is 81, this is 87, then we come back to 88 up here. So this is F8, and then this goes to FF here. So this is all 128 bytes defined here. Now, as we look at this right here, everything in this column is bit addressable. We can have a location called P1.0. Now, P1.0 happens to be port 1 bit 0. If we go back to our right here, we see there's P1.0 right there. Right there. So this is port 1. It happens to be location 90. And then this happens to be out there. But we can address it with P1.0. This is where that port occurs in memory. It's a special function register. So we'll see as we go down to this column, here's port 0, port 1, port 2, port 3. The 8051 has up to 4 ports on it. Ours doesn't have that many because it only has 24 pins, or 22 pins. So it doesn't have that many. We also have various other things. This is the analog digital converter 0 control registers right here. We also have, for example, other ones here. Here's our timer mode, timer 0, the lower 8 bits, timer 1, lower 8 bits, timer 0, the upper 8 bits, Timer 1, the upper 8 bits, the clock control, everything on this processor that we can control is usually done through these special function registers. So these are very important registers. We're going to be spending most of the rest of this summer session looking at controlling this processor writing code, but we need to know what these special function registers do. Okay. So, all right. That is the overview of the internal workings of the 8051. A lot there, isn't there? And you can see if I was doing multiple processors, every processor has a unique set. Everything we talked about thus far is common to all 8051 microcontrollers. As soon as you start talking PIC microcontrollers or 8085, 8086 microprocessors, the internal architecture is completely different. So every processor is unique in terms of that there. They're similar to each other. And once you understand one of them, understanding the next one is very easy. If you're an auto mechanic, for example, and you learn how to repair protons, taking that same knowledge and doing repairs on Perduas is not that difficult. They all have engines, they all have transmissions, but they are configured different. That's there. Same thing. If I look at the PIC, it would have a different set of architectures. They'll do things a little bit different, but very similar. That's it. So, all right. Now let's get into our addressing modes. There's 8 different addressing modes. We're going to talk a little bit about this. We will meet this afternoon at 2 o'clock, by the way. If there's enough of you here that there. I didn't want to lose this afternoon. It won't be long, but we're going to go through the addressing modes. I haven't really written a lab, but we'll go through the ones that are here. So we've got our register modes. We move from register A or B to A. That's all that does. This here moves the contents of A to memory location 30 hex. If there's nothing in front of the number, that means memory location, and that's the memory location in the data RAM. Remember, there's 3 different memory locations. If you don't say anything other than the number 30, the assumption is it's being moved right here. Right there is where it's going to be moved, right there. So it's going to be going this location. This is location 30. That's the first one we have free, right there. So when we look at this instruction here, we're moving the whatever's in the accumulator to memory location 30 hex, right there. Now this one's a little bit confusing because when we put the ampersand in there, that means that the address is stored in R0. And we're moving, that's there. So in this particular case, R0 is going to contain the 30 hex. That's an R0. That's a location. So this is the memory location that's stored in the register, right there. And we're moving the contents of R0, or the memory location pointed to in R0 is moving to the location that's there. And this is one where I think you really need to see it in a demonstration working on a lab, is that we're going to move 30 hex into R0 and then move whatever's in A and use this right here. And we can do this backwards. We can do this is actually an add, but I'm sorry, this is an add. So it's going to take whatever's in 30 hex and add it to the accumulator and leave it in the accumulator. So what we're seeing here, and I'm not going to spend a great deal of time on this because I think we'll look at this in a lab, but R0 is going to contain, we'll say 30 hex right there. R0 contains 30 hex. In memory right here, at location 30 hex, I'm going to put 15 hex right there. And A has 1, 4 hex right there. Hex right there. I execute the add A R0. What this does is it looks at R0 and sees the 30 and grabs the 15. R0 contains the address. It points to this right here. So this is going to contain, after this instruction, A is going to contain 29 hex. Right there. This is what it's going to contain. That's there. There. And so this particular addressing mode is confusing because I'm looking at 3 different locations. Right there. Now the advantage of this is I can then increment R0 and grab the next one and add up a column of numbers. I can write a very short little program to add up 10 numbers that are stored in 30 through 39. Right there. And I want to add them up. And I can write a very simple little loop to do that right there. So up there, and we'll look at some of those instructions on how you would do that there. But getting back to this right here, let me get back to my slides right here. Right there. This is the indirect right there. Now this one's a little easier. This is the one we did before. If you have the number sign, that means just a median. All we're going to do is add to the accumulator the number 80 hex. And that's there. So we've got 3 symbols that we have to look at so far. And that is no symbol, which means we're looking at a direct address. We're looking at the at sign, which means the address contained in that register. And we're looking at the number sign, which means the immediate data. So as we look at, and they do completely 3 different things. And then we also have the registers look very much like up there A and B. Remember that our registers are very, very limited on what we have. A, B, R0 through R7 is typically what we would use right there. Now, relative and absolute, these are normally used with jump commands. An S jump means jump ahead, or jump within a very small range. Absolute means that it could be farther away, right there. So, and then long means that we're going to go even further up there. So we get absolute right there. So again, we have multiple up there, and we've got this right here. Move C is actually kind of a funky one. That's actually moving it from the program data. That's there. We can actually store data, and we're looking into A, the address that's an A plus the program counter. See, that one's even more messy. Right there. Because what that's saying is that we're looking at the location where we're at, it's where the program counter is, plus the contents. We're going to grab the number 3 places ahead or 4 places ahead. We're going to add that to A. I don't use this one very often in writing assembly language, but we'll look at that there. So, all right, these are some examples. We're going to kind of go through these. That there, I don't have a lab written up, but we'll just kind of go through various ones. Here, we're just going to move A to R0. That's all that does. It's just that there. It must be specified prior to the instructions. We'll talk about that there. Here, we're moving direct addressing here. This is actually a direct. Port 3 is actually a memory location in the special function range, right there. And we're moving its contents to A, is what that's doing. Now, in terms of real life, is we're looking at the port and we're reading the data on the port, right there. Here, we're moving the contents again of memory location 20 to the accumulator, right there. These are our direct addressing modes. So we use the direct addressing mode more than you think you do, because that's how we move things in and out of the port, the analog digital controllers, how we send things out the serial port, because those are all special function registers, and they're specified up there. Indirect, that there, uses a pointer to hold the effective address right there. So only registers R0, R1, and the data pointer can be used right there. Right there. So this is a key difference right here. R0 and R1 will only address up to an 8-bit address. 8-bit address goes between 0 and what? 256, right? Which should be enough. The data pointer can hold a 16-bit address. So typically, that's there. This is what you would use. Now, notice here, there's something different about this command right there. You might see what's different about that. There's an X there. That X means that it's looking at external memory. Right there. Going back to our discussion right here, we have this external address space, right? And whenever we want to address that, we have to use the move X command. That's how we tell the assembler that we want to look at that there. We have 3 different memory spaces. If we use the move command, we're talking right here. This is the move command. We'll grab that one there. This is the move. This typically uses the move C if we want to use that there. And this uses the move X right there. So we've got that there. So as we go back and we look at this right here, we have the move X, and we also use the data pointer and not R0 and R1. And the reason is R0 and R1 are 8-bit registers. Internal to the 8051 is only can access 256 bytes. R0 and R1 are more than adequate. But as soon as we go to the external memory, we want to use the data pointer to point to where our data is, because that's a 16-bit register. So not only as we look at all of our registers here, right here, we'll see the data pointer should be somewhere. Scam address register. I'm not seeing the data pointer. It's somewhere in here, down here. Yeah, right here it is. That happens to be a 16-bit register right there. So the size of these registers does make a difference right there. So, and remember, externally we can go up to 64K, which 16 bits will address right there. So as we look at the indirect, we throw in another curve here, is that we now have a separate command for moving to external. Our processor has got 256 bytes on the external. If you're going to use the external, then you have to use the move X right there. Our immediate is actually fairly straightforward right there. Keep in mind the size of registers if you're doing this. In other words, this is moved to the data pointer, and we give it we're giving it a 16-bit number. Remember, I think I made the mistake that we have to put the 0 in front of anything that starts with a letter. But that's memory. We're moving FE00 into the data pointer right there. Here we're moving 30 hex into we're adding that to the accumulator and store the result in the accumulator. So that's it. So this number, the number sign indicates that we're doing an immediate. The @ sign means we're doing indirect. And nothing right there means we're doing direct. So we have our 3 different types of addressing mode: direct, indirect, and immediate. Those are our 3 primary ones that we look at right there. Relative addressing is usually used for jumps right there. Right there. Here's a short little loop like we've done that there. This is right here. Get there. So we have short jumps and we have conditional jumps. Here's a loop, something very similar to what we did. We're decrementing A and we're jumping back to decrement if it's not 0 right there. We have to assume that we had a move to A number 0FF beforehand. So that would do it 256 times. If we want to do it 10 times, we would just do move A 0AX right there. And that would do it 10 times right there. So before this here is where we would specify how many times we want to go through this loop. Now we don't have to have them back and forth. We can go through and we could do an add instruction, for example, right there. So we can use the number, grab the data, add it to A, use the next number, add it to A, and then we could decrement, say, for example, R1, and use R1 as our data pointer for indirect addressing. So we've got all kinds of options there. The only thing is we have to make sure that our code is short in between the jump. In this case, they're right next to each other. But we only have 128 bytes to play with, plus or minus, right there. So we can't have a lot of code in between that there. So, there. And we can do the short jump. That's it. Absolute call means that we don't know how far away it is. Associated with this, or the absolute call and the absolute jump. Right there. That gives us within the current 2K byte, or 2K up there. So it's got to be within 2K. Right there. So the absolute, and this is an A call or an A jump. An A call means we're calling a subroutine, which will have a return back. Or here we're going to be doing, right there, this happens to be a label, and it has to be somewhere within 2,000 bytes of our assembled code. That's there. Then the long is going to be 16 bytes. That's there, bits. That's there. Long call, and that means it can be anywhere in our program memory right there. So when we look at relative, absolute, and long addressing, those are used predominantly for jump or call commands. Right there. The relative is usually not used for a call. It's usually used for jumps or conditional jumps. Right there. Short jumps or conditional jumps. Right there. Absolute is used for calls and jumps, and long is used for calls and jumps. And the difference between a call and a jump is a call is you're calling a routine, and at the end of the routine you have a return and you go back to where you called it from. A jump is just a go-to. You just go there. I look at a call as a return ticket. You buy a return bus ticket from KL to JB, right? So you're going to JB for 4 days. You buy a one-way ticket, you're moving to JB. Right there. Previously when I came to Malaysia for a visit, I bought one round-trip ticket. I was doing a call. I was going to KL visit, my wife's family, do some sightseeing, whatever. And I'm going to be in Malaysia for 3 weeks. So I'm going to do a series of things. But then I go back to the U.S. This time I bought a one-way ticket. So I did a jump, a long jump. And that is a long jump from central Indiana or northeast Indiana, Midwest U.S. to Kuala Lumpur is about as long a jump as you're going to make. Right there. That's a long jump. But a call is a return ticket. You're at the end of the routine, you return back. So if I do a long call to a routine that I call delay, then at the end of the delay I do a return. Right there. So we have long call, absolute calls, and long calls, absolute jumps, and that's there. And the only difference is how far you're jumping. Right there. You could use the long every place you want. It works perfectly fine. But if you use the absolute, sometimes you'll get an error from the compiler or the assembler saying it's out of range. That's there. So, but again, you look at the instruction here. This is a 2-byte instruction. This is a 3-byte instruction. And memory is expensive, so you try to use the smallest instruction you can get away with. There. Index is a very complicated one. It's not super complicated, but it is a little bit complicated. Is that it's usually used for lookup tables, and the sum of 2 registers forms the address for a jump or call or a move C. Right there. That's there. I don't want to get into too much detail on it, but what this is we're moving 8, and then we're moving to the data pointer, the start of our address, and then we're moving into the C, our move C. We're doing get the target value from the table, start address plus the offset. We're doing 2 adds. What we're doing here right there is is we've got a table right here that contains data. Right here. This is a table right here. And we'll just say, I'm going to just say, throw a number down here. This starts at F0000, right? Or no, not too many zeros right there. And it goes down to F0FF right there. So I've got this table right here. It's 256 bytes long. 250 and 256 bytes right there. 256 bytes there. I load into move to the data pointer 0. This is number sign 0F000. That loads into the data pointer the start of this address right here. I do a move into A08. We'll just use 08 right there, hex right there. And we put a number sign there. So this is memory location F008 right there. And we'll say that's 23 right there. And then I could do a move C A. Let me get the instruction correct here. Right there. From the table, start address plus its offset right there. So in other words, what we're doing is we're saying at this point right here, right there. So it's at plus data pointer. So we're taking this right here and we're moving that into A right there. But we're taking and we're using the 8 from the accumulator plus the F000 from the data pointer, and we're adding those two up. And it's a way that we can address tables right there. Right there. It's not something we're going to do a lot in this class, or if we do it at all, we'll just to see that how it works. We're not going to be doing it for too much of our programming. It's used a lot in addressing arrays. Right there. If I want to address the fifth element of an array, and everyone's had C programming, right? You've had C, so you know what I mean by an array, right? So, an array is, I've got an array called student ages right here. And I've got 0 to 30 students right there, 31 students in this class, right? And student 0 is 19 years old, student here is 22 years old, 19, 21, 27, we've got an old, 26, you've got an old guy in the class here, that's there. And we've got all of our ages here right there. So if we want to address this student right here, this is 0, 1, 2, 3, the fourth student, this is student age 8. I don't know why I'm age 4, right? Right there. So when we look at this, this is our data pointer is pointing to the top of our array, and this is what we load into the accumulator to tell us it's the fourth element of the array. So when we look at this indirect mode of addressing right here, if you look at it in terms of arrays, you can see where it's very, very, very powerful if you're going to address arrays. The good news in assembly language, we're not going to do arrays very much. That's there. It's awkward. Doing arrays in C is very, very simple, right? Or it should be simple. But you got to remember what happens when you write a program in C. It's then translated into assembly language. That's there. So by allowing this addressing mode, even though it's awkward for us to use it in assembly, it makes it very, very straightforward. It makes it straightforward for the assembler or the C compiler to generate the assembly language code using that there. So if we wanted to, for example, find the average age of a group of students of a class, we would add up all 30 ages and divide it by 30, right? That's the way we would find the average age in a class. Well, if we didn't have this addressing mode, that would be a real long program in assembler. That's there. In C, it's a very straightforward program. I could write a C program that's fairly straightforward. That's there. That find the average number. Doing the same program in assembly language would be a little bit more complicated, but it can be done using this addressing mode right there. So I think I'm going to wrap up with this. What we're going to do this afternoon is I'm just going to be basically going through these slides, and let's just go through a short little demo on how it works. That's there, and you just follow along with your boards right there. There won't be anything to turn in, but you'll need to bring your board. You do need the boards. I don't have any boards. All the boards have been collected. That's there. So I got one board for me to use. So if you don't have a board, you're going to have to work with somebody else. That's there. So if you left your board back in Combone and you're going to go back home over the weekend to get it, so you have it next week, then you're going to have to work with someone else. That's there. There won't be anything to turn in for this lab, but it's more going through the demonstration of that there. Because some of these actually make more sense when you see them on the registers right there. So with that said, I'm going to hopefully have there. Okay.